Hey everyone. So we will wait a couple of minutes until we start the presentation, and then go ahead. If you have any questions, hopefully you can see the kind of Q&A or the chat, and kind of ask questions in there about anything we're discussing, and we'll try to answer them, or just ask in the chat. But probably easiest if you use the Q&A. So save that. But we'll get started at about 1:20. If you all don't mind sending, was it event chat disabled? You all could ask a question in the QA, somebody, to make sure you all can hear us. Good test. I guess it says event chat is disabled. Interesting. Okay, so.
For me, it just says no messages yet, so.
Okay, must be Blue Jeans. Test. Great.
Yeah, sweet.
Publish that. There we go. So. Good to hear. Cool. Yeah, feel free to ask any questions. So I guess we can just introduce ourselves in the meantime. I'm Joe. I'm actually now a graduate from Georgia Tech. I graduated this past December, a couple of weeks ago, as an electrical engineering major and robotics minor. And I've been a part of RoboJackets for all 4.5 years, technically, it's been. So worked on a bunch of different robots. And I'll have to be honest with you all, I worked on FTC in high school, but then I've kind of worked on tons of other robots, primarily self-driving cars. I've made a couple of platforms that can carry people and drive around figure eight courses, and made a couple of RC car sized platforms too. So, Dan, you want to give some background on yourself?
Yeah, so my name is Tan Tanj. I'm a third-year electrical engineering student, and I was an alum from FRC Team 4189. I did that all throughout high school, and this is actually my second year in RoboJackets because I transferred into Georgia Tech. Really like helping out at the events, so at the competition. So kind of sad that we won't be able to do those this year because those are always a blast. So
Yep.
like to help out where we can.
Definitely.
And yeah, so we're both on the Robo Racing team at RoboJackets, and you can go to robojackets.org to check out some more details and pictures of what we get up to at our different teams.
Yep. Do a bunch of different competitions. So we do some self-driving car competitions. We do battle bots, which I guess a lot of people know. I bet some of you all have had the work you've done at FRC compared to battle bots. That's the common thing. Like, oh, you do robots? Oh yeah, battle bots, right? We do soccer playing robots. They play 6v6 autonomous soccer. We have like an off-road navigation robot competition that kind of goes over rough terrain and has to navigate like in grass fields and stuff. And then we have our sumo robots, which you put them on these metal plates, and you might have seen videos of them, but they go incredibly fast. and have to push each other off the field. So the team Tan and I are on, we work on the self-driving car competitions. All right, looks like it's 1:20, so I guess we'll go ahead and get started. So like I said, my name is Joe, joined by Tan, and we're going to kind of go over just a little bit of background on FRC electrical systems. This is kind of pretty high level. Talk about some of the different subsystems that are involved, and go from there. And like I said, feel free to ask any questions in the Q&A as we go through, even if one of us will be presenting and the other one will try to be answering questions at the same time. All right, so we'll start with the power system. Most robots can't get too far if they aren't turned on, so it's probably going to be a good place to start. So we're going to start with the power distribution panel, or the PDP. So it receives power from the battery and the main breaker. So that's kind of example one right there. And it provides fused battery power to different components that are on your robot. So if you have anything on your robot, you want to go through this device. So we'll get into fuses a little bit later, but fuses help protect the wires and your components from pretty much becoming a small fire. So it's really good to use fuses in any design, but of course for safety reasons, all FRC robots are required to use this PDP to kind of handle all that fused power. So like I mentioned, motor controllers, the RoboRio, the voltage regulators, and the pneumatic controllers. It's also used to terminate CAN rings. So CAN bus is a communication bus that many of you may have used before or not, but it's actually the same communication method that's used in cars to communicate with the steering wheel. It's now a lot of times drive-by-wire, all the way down to the accelerator, to the motor, sending information back and forth to kind of make everything work and work reliably. So you may see the CAN bus used on your motor controllers and some other parts and sensors. So good transition. So motors. So there's two main types of kind of large-scale motors that you'll probably see. Those are brushed motors and brushless motors. So that brush versus brushless on a brushed motor, there's these little kind of parts inside that help make the electrical contact, and it allows the rotor to spin. So brushless is just a different design that doesn't have those brushes. So brushless, brushed, that's the distinction there. And there's a bunch of different types of motors that are offered that you can kind of incorporate into your robots. Sim motors, the Venom 755 Redline, and the bag motors. Their brushed motors themselves are pretty simple in design. So it's pretty simple to wire them and control, and they're often a lot less expensive to buy. So first getting in, and for a long period of time, they were kind of, I think, one of the only options. You can only get brushed motors, but as kind of drones have taken off, and hobby RC cars, we were talking before, the cars that Ken and I work on, the RC cars, they use brushless motors instead. So we'll get into brushless motors. Like I said, the difference is just they don't have this brush, but from the outside it just looks like a motor. The options are the Neo, the 550, and Falcon. They're better power weight ratio than the brushed motors, but they require a little bit more complex control. They usually have 3 wires coming out of them. If you're kind of looking and you just want to understand what the system is, usually if you see a motor with 3 wires, this usually means it's brushless, and brushed wires is usually 2 wires. So having motors is great, but being able to control it is a little bit better. So as I kind of mentioned, the 2 wires versus the 3 wires in the motor construction, you'd think, oh, okay, I guess you need to have a different motor controller, which is correct. So we have for the brushed, as I mentioned, brushed were really popular for a long time, so they're the most abundant options from different companies. So we got the Talon SRX, Victor SPX, Spark. And this, to be clear, all these kind of products that we're listing, this isn't every single option. There are a couple more options if you want to look at the game manual. You can reference the 2020 one, but they haven't had many major changes in terms of the electrical system. I think they added a new motor option, so just take a look at the 2021 manual, which hopefully you all have access to on this. But as I was saying, yeah, there's a bunch of different options. I guess there's the Spark is a lot more simple. It's kind of just like a AWM, pretty simple. Some of the other, the Talon SRX, they have the CAN bus option that we were talking about for the PDP, where that has to get terminated, and this allows for usually more features, doing motor speed control and sometimes encoder feedback. So there's kind of a wide range of motor controllers. You kind of have to figure out what you're trying to control. Is it your drive motors, or is it an actuator for whatever the design may be? You can kind of look through which motor controller would be appropriate for the features that you need. But if you have brushed motors, get a brushed motor controller. And if you have a brushless motor, I think your only option, pretty sure still, is the Spark Max. That is, as you can kind of see in that picture, the 3 wires, the A, B, and C, at the bottom right. That's those 3 wires, like I was saying before. That's I think your only option. I'll get into a little bit in a second, but so if you want to use brushless motors, that's kind of what you have to go with. But I guess a weird exception is, we'll say a special exception, how about that, is some motors actually have, we talked about motor controllers and we talked about sensors, so some sensors could be like encoders or Hall effect sensors for measuring position or speed. Some motors actually have all of that built into one package. It's the motor controller, and sensing, which is pretty nice. It's very compact. Could be a bit more expensive. This is kind of design trade-offs that you're going to have to make as a team. So a couple of options include the Falcon 500. That's a brushless motor option. So if you want to get into using the brushless motors, this might be a good choice. You don't have to worry about getting new motor controllers and all that. And the Venom Smart motor, so it's like a sim motor, but it has some feedback, which is those encoders that I kind of mentioned before, all kind of built into one package. So it's usually just power and communication, which is pretty nice for kind of wiring and just being concise. But kind of have to keep in mind, it may be more expensive if you have to replace a specific part as opposed to just replacing a motor or replacing a motor controller that goes bad. So a couple of features, kind of already alluded to it a little bit, but motor controllers with CAN capabilities, so it's like the Talon SRX, Victor XPX, and Spark Max. They have usually configuration settings that you can set over CAN. You can do something called closed loop control. So you use sensors that are kind of plugged into the motor controller to accurately control the motor properties. So an encoder or Hall effect sensors primarily are the sensing methods, so that you can kind of get that information and control your motor a little bit more accurately. We have another talk about controls that we're going to record all these videos that if you want to go back and kind of look at that, gets a way more in depth into kind of what control is. And then another option is the follower mode. So this is kind of useful if you have 2 motors attached to the same mechanism. So you can kind of just send a command to one and they both follow the same speed, which is pretty cool for drive systems, right? If you have 2 motors that are on one side, you want to send them the same motor commands. That makes a lot of sense to go the same speed, so that you don't have offsets and cause problems for the mechanical team or the software team. So those are kind of big options. Like I mentioned, CAN is usually the communication method of choice. Sometimes there's PWM options as well, but it's kind of like the more smarter in terms of feedback, control loops, that kind of thing expands for that. As I mentioned, fuses are pretty important. So the job of a fuse is to limit the amount of current flowing through a circuit at any point in time. And the load, which is what's kind of drawing the current, this determines how much is drawn. So if you have motors that draw more current, then they apply more torque. That's kind of how that's related. For the PDP, you have 8 slots for 40 amp loads and 8 slots for 30 amp loads. Kind of just like a recommendation based on some of our members' experience that they had. It's good to allocate the 40 amp loads to the sim motors and the 30 amp loads to the 775 redline motors. And from experience, the redline motors can kind of pretty easily burn out. So kind of just keep that in mind in terms of figuring out numbers of spares and stuff like that. So fuses, like as a function, are kind of thermally triggered. So really what it is, it's like a little piece of wire that if there's too much current, it will melt and it will separate the two connections. And the amount of time it takes for that melting and separation to occur is dependent on the amount of current flowing. There's a lot of different options you can get, but in terms of the load time or the amount of time it takes, motors often kind of have a lot of inrush current, so it's a lot of current at the beginning, but then when they start spinning, overcoming friction, stuff like that, once they're spinning, they're usually a lot lower. So it's good for the fuses to be able to handle that, maybe that initial spike, as long as the wiring and everything is capable of it, and then to kind of continue as normal. That's totally fine. So yeah, fuses are really good things to have in any electrical system. I know on our robots we've been messed up by not having fuses, so good to learn how they work and when to use them, which is pretty much all the time. So, all right, I'll hand it over to Tan for control systems.
Hey, so yeah, now we're gonna talk about pretty much everything that's on the right side of this picture there. Well, we can go on to the next slide. So essentially the RoboRio is the brain of the robot. It is what is going to do basically all the onboard processing of telling the motors what to do, and it is what the software team is going to be writing the code for, and essentially what is going to send out the signal for your different parts of your robot to do different things. And so it's a processor with a variety of communication options. Shown on there is, like we've talked about, it has PWM CAN and then also a digital I/O output. And then finally, it also controls the robot signal light, which is there, very important, required by the rules to know what state your robot is in, if it's playing a match, if it's disabled. And so that is very important, and make sure you have that wired up correctly. You do have to, if you look there on that picture, you have to put a little jumper over to between the outside terminals on the robot signal line. So I just wanted to note that, and it's shown how to do that when you're putting it together. And so then we can move on to the different types of communication options. So like we were just talking about, maybe you guys were a little confused on what those different were. So these are basically the different ways that you can talk to the components that are on your robot from your RoboRio. And that's what there is. Essentially, the simplest one is the digital I/O, which is either basically on or off. And it's useful for reading switches or encoders. And it is, so essentially, if you had like a limit switch, if you had an elevator and you wanted to know when your elevator got to the top and you wanted it to cut off so it didn't go off the end, that would be, that would basically turn on when you get to the top, and then your RoboRio would know, and you could use that in the code. And then the next one, which is the older style of connecting to the motor controllers, is the PWM, which is pulse width modulation. And so essentially, if we think about it, we have this this power distribution board, and it's connected directly to the battery. So it's giving full power to the motors. Basically, if you were to hook the motor straight up to it, it would give it full power. But we essentially want to cut that down, because we don't want the motors to be full speed all the time. You know, when we want the robot to turn, we want the left side to be going slower than the right side, or the right side to be going slower than the left side, so that the robot can turn. And so that's why you need the motor controller in there. And so basically, PWM and CAN are two different ways to talk to these motor controllers and essentially control the motor there to slow down, to reverse those type of things. And the big difference is essentially in how they are wired up. So if so the PWM is basically going to be a wire going from the RoboRio out to each motor controller, kind of like a tree with its branches. You could also put a splitter in there to have two different motors controlled exactly the same. So kind of basically like a tree there. Whereas the CAN is a two-wire signaling protocol, where it's going to be basically a big loop, and it can do some more complicated things. And so then we can go on to the next slide as well. And basically that's what I was just saying. So they're all daisy chained together into a network. And it has to start at the RoboRio and ends at the power distribution panel. And then basically everything is added individually in there in the middle. So if we go on to the next slide, we can see a picture of it. And then so that's showing you essentially start it at the RoboRio, and you would go out. This showing here in the middle is the pneumatic control module. We're not going to get into too much, because that gets a little bit more complicated, and of how the pneumatic system has to work, and just make sure you're following all of the rules that are detailed in the manual for using a pneumatic system, because of course when you have a compressed air, things can get a little bit more dangerous. So you just want to make sure everything is safe. So this is showing you have one device in the middle there. It basically goes in one side and then out the other, and then ends at the power distribution panel. And it's actually looking, it has to cross through a specific resistance at the end there, so that it knows that it's at the end. And so essentially, if you wanted to then add in some of these CAN-controlled motor controllers, you would put them in the middle of the loop there. And so instead of basically having a tree going out with PWM, you would have a loop going around your robot out from the RoboRio and back to the power distribution panel. So that's just something to think about when you're considering how are you going to wire up these different motors, because you can only have one CAN network. So if you were going to have a motor out on the end of an arm, you would have to run the wires out there to it and then back. Whereas with PWM, you would only have to run the wires to it. So then we can move on to the router slide. And so the last thing here is the router, and what we would definitely recommend for the best way to power the router is to use Poe Injector Cable that is included in the kit of parts. It is that orange cable there, and that stands for Power over Ethernet. So the Ethernet wire is just basically how the router, which is basically taking the wireless signal from the control computer of what you're doing with the joysticks, and then telling the RoboRio what that is. And so you need to have the router needs to be powered from the battery. So it has to get a 12-volt power source, and so that has to come from the VRM, the voltage regulator module. And so the easiest way is just to use this PoE injector cable. You can separately power it with the barrel jack connector that comes with it as well, but it's just easiest to use the PoE injector cable because even though not this year you won't be going to any competitions, but once competitions are able to resume, just a good tip for the future is you're going to have to be taking this router out because you have to go get it configured for the field when you go to a competition, and so you want that to be easily able to removed and taken off the robot and then put back on, and so you don't want to be fiddling around with anything. So you have to be very careful that the PoE is basically adding power to the control signal. To the same connector so that it only has one connection to the router. And so you want to be very careful that you are plugging in the powered side to the router and not plugging in the power side to the RoboRio. So like that picture in the top right there on the left, you're going to use a male-to-male Ethernet cable to go from the RoboRio to the female side of the PoE injector cable. And then the male side of the PoE injector cable goes into the router, and then you plug in the barrel connectors that are coming out of the end there into the VRM. And then that's pretty much all for the control system. So we can move on to the wiring.
Great. So wires, they're simple, but they're more complex than you think. So there are kind of two main options when it comes to wires. You can get stranded wires. So what that means is there's small little, we'll say mini wires inside the big wire. They're all connected together, and they are just kind of small strips. And then there's solid core, which is just kind of one piece of copper or aluminum or whatever material it's made of, one solid kind of chunk. So highly recommend using stranded wire because of just kind of material properties. It is a lot easier to kind of move it around without it breaking. So solid wire, if you have like say a metal coat hanger and you bend it back and forth enough times, it will break. The same thing will happen with your solid core wires. But your stranded wires, just because there's a little bit of room to move around in that plastic, your insulation, some other aspects, it can handle a lot more stress. Probably still wouldn't recommend bending it back and forth a ton, but it can kind of handle that a little bit more. So, moving up actuators or just kind of moving things around when you're trying to get at something to fix something, feeling okay that you can bend it and move it temporarily or permanently is kind of good to have. So highly recommend stranded wire for that. Another good thing to do is use color codes that are consistent. So, on the outside of these wires, there's the plastic housing or insulation. So definitely a good idea to kind of be consistent with your wiring color. Don't mix, if you're going to have red to be your positive and black to be your negative, keep it that way. Don't sometimes do that and then switch it to black and black and then, red and red for positive, negative, right? So try to be consistent with your color codes or else somebody may, unwire something incorrectly or plug something in the wrong way and cause hopefully the fuses to work, but you don't want the fuses to work all the time. Might cause a small fire. Probably won't happen, but it's always good to use consistent color codes to kind of reduce the chance of that happening. And then the last kind of major component of wires is the gauge. So this is kind of the thickness of the wire. And this kind of determines the amount of current that can flow through the wire. So we kind of talked before, fuses are little wires really that melt and separate. You don't want your wire to connect to between your battery and your motor, or your PDB and your motor controller, to act like the fuse. You want the fuse to act like the fuse. So in order to do that, make sure you're using the correct wire gauge. That's the thickness, to kind of prevent that from happening. The game manual actually gives you really good, pretty clear definitions of what wire gauge you should use for what current ratings. So it's always good to kind of reference that, and probably just stick with that, because then you'll reduce the chance of these small fires. Another really great thing, simple but it's super useful, is connectors. So connectors I would recommend using for every single kind of component that can be removed, when reasonable. But it allows you to kind of easily replace. Say you have a motor that blows up, right? You can just unplug, plug in a new one. If you have the same connector, make sure you don't have just one set of the motors with the connectors on it. Make sure if you're using a connector, all of them have the same connectors if they're all designed to be plugged in and replaced and swapped out. Make it so easy so that you can just unbolt it and unplug, and you don't have to go and get your wire cutters out and take off insulation and do a bunch of other steps, which is super important at competitions, or just even in the shop, just testing things and replacing things. It makes it so much easier. So can also allow for wire lengths to be changed pretty easily. So if you have kind of an extension cable type deal between two parts of the robot, you can just crimp two sets of new connectors, unplug and plug in a new wire, if the mechanical design changes because you learned something while testing, right? So the most popular used in FRC is the Anderson power pole connectors, and similar to, we were talking about the wire gauges and the current rating fuses. Different power poles are designed for different wire gauges. So they have really tiny ones, and then they have ones that are like massive, and you're like, wow, it's pretty big for connectors. So make sure you pick the correct size connector for kind of the job, because again, you don't want your connector to be acting like your fuse. You want your fuse to act like your fuse, and make sure it's not melting. Kind of definitely recommend terminating your motor and your power wires with the power poles, because they're pretty easy to unplug and replug and replace things. And the last kind of important aspect in the kind of design process is a drag chain. So this is for sliding mechanisms, like an elevator of some sort. It's that black chain component. It keeps the wires organized in a moving mechanism. Like I mentioned, linear slides, it's super useful, and sometimes necessary. So you don't want your wires kind of flailing all about, and then one time you're moving up the elevator and it rips something out. Pretty catastrophic failure. These drag chains can really help simplify and make it look nice and clean, but also prevent wires from coming undone and getting ripped out. Loop the chain down from the stationary point and then up to the moving point so that it kind of moves appropriately, as the kind of the drag chain is designed. So yeah, thanks for listening. If anybody has any questions.
Yeah, if we want to go back to the wiring kind of title slide with the picture of the kind of cable management, yeah, so we can talk about this. It's very important to keep everything neat and organized. Of course, you think it, you think you'll keep everything. You'll think when you start kind of laying things out that it'll all stay organized. Oh, it'll turn into a mess very fast. So see here they have basically all the cable, the cables going from the power distribution panel to the motor controllers and then out to the motors, all nicely routed and zip tied down. That's very important. You do not want any wires that are able to move around freely. You don't want anything to be able to catch them, because you'll be surprised how much mayhem actually can happen on the field, and so you want to make sure everything is nicely tightened down with zip ties or kind of cable management devices, and like the drag chain that Joe was just talking about. And you certainly want to make sure that you have everything connected with connectors that you can unplug it and replace it without having to take all the wires off. I have certainly made the mistake of just directly soldering wires on, but you want to make sure everything is put into a connector. Like here, they have the Anderson power poles between the motor controllers and the motors, and then I think they're using Dean's connectors. Does that look like, Joe, on the motor controllers? Those are also pretty good ones.
Possibly.
Yeah.
Think
Another
so.
good tip that's shown on the picture here is covering up the unused ports on the RoboRio. You do not want to get any metal shavings in that RoboRio, even though it's covered. The outside's covered up with plastic. You still don't want to get anything in it because it is very valuable. Honestly, much more overpriced than it should be. And so anytime when the mechanical team is starting to drill holes in the robot, you want to make sure everything is covered up nice and neatly. And even if you want to use a vacuum to try to get any metal shavings or and then also make sure everything's certainly covered up. Another good tip is when something's not working for troubleshooting, I would say it's probably 75% of the time something's just not, well, maybe even more than that. It's either not connected or connected to the wrong place. So make good use of a multimeter on the continuity setting to make sure that what you actually think is connected actually is. That can certainly be helped by putting labels on the wires as you are working on it. You can buy little wire labels to have a kind of a key for which motors are connected to which motor controllers, and then which ports on the power distribution panel, because things will get it'll get more complicated than you think it can. And that was kind of everything I had. Do we have any questions? Yeah, I would say that stranded is definitely the best way to go for the power systems. I guess maybe on some of the control wires it could be solid core, but it's you definitely want to have everything nicely routed, so you don't want any stranded wires breaking.
Yeah. Remember, sometimes for crimping, I guess no, it's also for wires that don't move around like at all. You could, if you have solid core wire in your supply, don't go and throw it away. It could be used there, but kind of going forward when you're purchasing wire, it's good to kind of stick with the stranded, in my opinion. So for the question about wiring wires under 24 gauge, so they're breaking because they're really thin. Sometimes you
Yeah,
can go
because the
ahead, Tan.
minimum wire size for the signal level circuits is 28. So that's what that's probably for.
Yeah. So um, if the wire is breaking, that may be a good idea to kind of they have thicker insulation wires, or even they actually sell cables that have multiple sets of wires inside. Um, we were saying stranded wires, they're small wires and they're all separated, or they're all connected together, but they actually sell kind of cables, be like an HDMI cable, right? Don't use an HDMI cable. It's a really expensive way to source your wires, but that similar concept of they have really small gauge data lines, but they're in this larger plastic of sheet. Maybe it could be a good idea to buy those for your data lines, because that also makes the wiring really simple because it's just one little bit larger cable as opposed to these really tiny wires that are kind of going all over. So you can do that, and you can also just get even the recommendation maybe up to 28. You can just go a little bit larger on the cables. As long as you can still, crimp your connectors, is another kind of good thing to keep in mind when you're kind of crimping connectors. There's gauges, kind of mentioned on the connector section. There's the gauges that the wire ranges can kind of go through. So it can be like, 12 to 16 gauge wires can work with this crimp. So keep that in mind. But you could kind of go a little bit larger on your cables. The electrons are flowing the same, right? It's not like it'll be any more restricted or anything. If you just go a little bit bigger, if you have the issues, if they're breaking. But it may be, wires aren't always designed to bend back and forth. Oh, that's another thing. They actually have even higher strand count wires, which at that lower gauge may be kind of hard to find, but I know at like the larger 12 gauges, they call it wet noodle wire, and it's super high strands. It's like you can see them, but they're still incredibly small. But it's so flexible. It's like a wet noodle, which is where the name comes from. So there may be an equivalent, super high bendable cable for the specific use case. You kind of just have to look around for when you're ordering cables.
Yeah, I'm not sure if what your problem is they're breaking when you're putting them in a connector or what, but you certainly want to make sure that that when you wire down, when you basically are connecting up any wires that you don't put any extra strain when you're plugging it in, like if you've got an arm that's out here moving, you don't want it tugging on the connector, so you want to make sure you plan for some extra space there and have it tied down along the wire instead of putting the strain on the what it's plugged into.
So I'm typing out my answer. It's a little bit confusing, but for some reason, on wire gauge, the larger the number, actually the smaller the wire diameter. You can look it up what the definition of the wire gauge is. It converts back to some imperial unit, but so like a 12 gauge wire is way bigger than a 28 gauge wires, which is a little counterintuitive. But which I guess then makes it a little bit difficult when I say higher gauge wire. In actuality, it probably mean larger wires. But if the number is really large, it just means it's a lot smaller, a lot thinner, and it can usually only carry a lot less current safely. But it also is a lot lighter and oftentimes easier to put places. So. And in case you all missed it, there was a question, will we have access to the presentation later? And if so, where can we find it? as I mentioned, we will be publishing a recording of all the presentations into the RoboJackets YouTube channel. So you can kind of check those out and watch some of the ones that you weren't able to make it to, which I guess is one of the nice things of the online format. You can go back and watch some other videos.
Yeah, and then also definitely check out the how to wire a robot guide that I put the link to on the test question, but it's also linked in the manual when talking about pretty much the wiring rules, because it walks through in a lot more detail with some really good pictures of actually how to put these connectors on, specifically on for the wire, the big wires coming from the battery, going through the emergency stop button, which is very important. You want that to be definitely very visible on your robot, but then you also don't want it to be easily accessible, because you don't want other robots to be able to hit it and turn it off. And then that goes to the power distribution panel. So if you've got a brand new equipment, then you'll have to put those on yourself. So it walks through how to do that, and then pretty much through. There's also some more details about the control system stuff, and then also doing the pneumatic system. So it looks very well detailed and nicely put together. So definitely check that out as you're going through it, and hopefully we were able to help you all a little bit, just kind of getting familiarized with the different parts, and once you kind of understand how it works, I mean, pretty much everything kind of almost works just a very similar way for like the robots that we work on. It's a very similar system from the ground up. So
Yep. And to be honest, I'll have to admit we probably take a lot of inspiration also from the robots that we work on in FTC, FRC, and VEX and all the other competitions that a lot of our members are a part of prior. We use a lot of the skills that we learned over the years and kind of bring them over to our own robots for sure.
Yes, and certainly definitely look up. I mean, there's nothing's ever done really for the first time. There's always somebody who's at least tried to do it before. So certainly look on Chief Delphi is the most popular FRC forum for recommendations for parts. That's something that we're not too familiar with because we've been out of it for a little bit, and so if you need some help of maybe what a vision processing camera to use, I'm sure there are many options out there now, and so definitely try to find somebody who's given it a shot before.
We had a question: how would you daisy chain an I2C? So I2C is very similar actually to CAN bus. There's a couple of differences just electrically in how the system works, but the same aspect is the chaining. So you can have all these things on the same bus. So sometimes it depends on kind of what product you're using. I'm not sure. It depends on if you've used stuff outside of maybe necessary FRC. But there's SparkFun has these things called the quick connectors, and they have two connectors on them. It uses I2C, and you have an in and an out. It actually doesn't matter which one you use. Their input and output is the same relative. So sometimes the devices have two ports, and you just kind of plug in one end, and then if you have another I2C device, you plug in the other end to that. Sometimes you kind of have to make your own splitter, effectively, is what it's becoming. And just make sure you're consistently using the correct, two wires on the same, part of the bus, so that you don't accidentally swap wires. That's kind of like the big thing to keep in mind. But compared to the CAN bus, you don't have to do the wire termination back on the, you don't have to go through the Roborio back to the, back to, oh my gosh, I'm blanking
Power distribution.
on the power distribution block. Because just, I mentioned electrical differences, there isn't a termination resistor on I2C. It uses capacitance instead, which, as kind of a point of knowledge, I2C uses the capacitance in loading the lines, which means that it may not always be the best option for really long cables. This is why kind of CAN is pretty popular in cars, going the distance up and back and forth across your automobile. It's kind of tolerant to that, but because it relies on some capacitance elements in the cables, very long I2C cables aren't always great. I2C is super good for when you have stuff right next to each other, all mounted together. But long cables you may run into issues, and it's going to be hard to figure those out, to be honest. So not to say you can't use I2C, but just kind of keep that in mind. You may run into issues if you mount a sensor, all the way on top of a mast of something, and run the cables all the way down around your motors and back into your control box. You may run into issues, but in terms of the physical actual wiring, it's very similar to the CAN bus. There's splitter wires you can use, or they have an input output in your sensor. It really depends. All right, so I think we'll stick around maybe for 5 or 10 more minutes, and feel free to ask any more questions. We'll kind of just hang out. Could be about electrical engineering. We're both electrical engineers. Going to Georgia Tech, FRC, electrical things, whatever. But yeah, I think we'll sign off around, we'll say 2:15. Does that work for you, Tan? 2:20?
Yeah, that'll be good.
Cool.
Yeah, and really unfortunate for the seniors this year. Hopefully you guys are still able to have a lot of fun with the competition. The game design challenge seems pretty cool, but of course the competitions are always the most fun. So certainly, if you guys graduate and are interested in coming to Georgia Tech, definitely check out RoboJackets.
Yep.
We have a training program that you go through to really learn how to do all this type of stuff. Like we certainly don't expect you to have the knowledge coming in, and even of course, I mean, if you pick up some stuff in FRC, that's pretty cool. But you can pretty much learn everything you want to from scratch through the training program each fall semester. So so certainly, if you guys are interested in coming to GT, definitely check us out.
So we got a question. What made you guys become interested in double E, and is a good career to pursue? Well, as somebody who now has a double E degree, I'm going to say it is hopefully a good career to pursue. So what made me interested? I mean, I'll be honest, it was probably doing FTC stuff. I got into some Arduino stuff in high school. I got it as a gift from a family member, and I kind of did a lot of the tutorials on that. So super interested in that aspect of robotics. So yeah, that's kind of what made me interested in doing it. I would say I was into programming a lot as a kid as well, and I kind of wanted to be a full stack roboticist, which is you know, as and many of you all probably know in your FRC teams, it's not just uh, electrical, right? It's electrical, software, and mechanical. Um, so if I wanted to be a full stack roboticist, which would be understanding mechanical, electrical, and software, super hard to teach, to be honest, to teach electrical stuff to yourself. It's doable, but it's really hard. So I thought that was kind of a good thing to pursue. And as kind of just, I guess, uh, some further background, I'm actually starting my master's in, gosh, 5 days, couple days, the 14th. We start back up. So I'll be a master's student working on controls and signal processing, which when you think of an electrical engineer, you probably don't think of, you know, signal processing. It's something that you kind of find out when you go into it. Um, I've also worked on designing PCBs from scratch, primarily in RoboJackets, which I guess is more, traditional thing in electrical engineering. But there's kind of a ton of different options and different avenues that you can kind of take it with. And if you want to change it later, you can say, I'm an EE, I can do something else, right? I can do some programming stuff. I can do PCB design. I can do controls, whatever. So in my opinion, there's a lot of different avenues. So yeah, that's kind of why I chose it. Dan, do you have any
Yeah, so
background?
that's what. Yeah, I can definitely share a little bit of why I'm interested in it. So that's what I was on an FRC team. I started doing that in high school, and I was actually on the mechanical side, doing the CAD when I was in high school. But I then interned actually at my local power cooperative, the local power utility in my hometown, and that got me really interested in electrical engineering. So that's what I'm actually focused on, power systems, and it's actually pretty neat how much the grid is changing to basically be a big robot, with the smart grid technologies that are being implemented, with the grid automation. So um, essentially being able to instantaneously detect an outage and basically reconfigure itself so that the minimum amount of people will go out of power at a time. And then, of course, the deployment of solar and battery storage systems, that is kind of pretty much revolutionizing how you actually get power at your house right now. And so that's what I'm pretty interested in. And kind of the robotic side is showing that you can do tons of stuff as a double E. It's very, very broad, and that's what somebody had asked. Also, what is the coursework like? The undergrad coursework is certainly kind of gives you a little picture of these different areas in electrical engineering, and like like Joe was just talking about in control systems, in digital signal processing, in electromagnetics, in power systems, in microelectronics, so semiconductors and basically diodes, MOSFETs, all that type of stuff. Because you can do pretty much you can do all different types of stuff with it. So, and then also in software development, because to kind of it's super hard to wrap your mind around all of double E, and so it kind of the coursework gives you a broad overview of everything, and then when you go into your senior level electives, you really start diving into what you're interested in. So that's what I'm going into the power systems, and uh, that's what
Yep.
I definitely think it's a good career to pursue, because you can do a lot of different stuff, and from that you're pretty much always going to be able to have a job. And so certainly coming to Georgia Tech, you're going to learn a lot. You're going to pretty much learn things that you never even really thought about, and kind of you have your eyes open to what's actually really out there, and how kind of something like your cell phone that you don't really think about how it actually gets put together and works. So that's why I like it.
So we had a question, how would you start creating a PCB? I'm currently using KiCad now, but it's still a bit confusing. Yeah, so my first very simple answer is I would watch some YouTube videos explaining it and make a project, which is probably way easier said than done. So we being RoboJackets, use Eagle, made by Autodesk. So that is kind of another option. Frankly, if you kind of learn one PCB CAD tool, it takes maybe a couple of days, but, oh, okay, sorry. The initial learning version may take you a while. I would say it took me designing and failing at designing probably 2 or 3 PCBs until I felt comfortable doing it. So kind of if it looks confusing at first, it's because it might be, which is okay. But I would just try making kind of new projects, and just even simple ideas like I want to make a switch that turns an LED on and off with actual physical parts. So you can kind of look up, on DigiKey or Mouser, they have a lot of times the kind of the software representation of the parts that you can put into your tools, your PCB tools, or you can kind of learn how to make them from scratch. That also is pretty difficult. So what I mean by that is saying, taking a power switch and turning it into a representation that when you're a PCB designer makes sense on the page. It's CADing. So turning it into a physical thing into something that makes sense in a schematic, which is kind of your electrical connections, which is something I actually recommend making for your FRC robots. Overview, but it's good to have like a layout of what connects to what. Sometimes you can even label the wires too, if you have a labeler, and then you know what's connected to what. So that's a schematic, a part of the PCB, and then there's the board layout where you actually place the physical parts and then draw the connections together. So it's pretty simplified look at how it's made, but that's kind of the steps that go into it. So you have to make the parts to be represented in that schematic and that board layout, and then go through and make your design, your schematic, and then turn it into a physical board. Overall, that's kind of like the high level. So I would recommend looking at, like I said, watching some YouTube videos. There's some tutorials for Eagle, RoboJackets. We've made a bunch of videos on how to use Eagle. So feel free to take a look at those on our RoboJackets training YouTube channel. Guess I'll just.
Yeah, and you can also look at the RoboJackets GitHub, because we have the slides there for going through and the source files for going through our training for putting together a PCB. That's what Joe's talking about. That certainly picking the components is for me the most difficult part, because it's if you don't know, if you don't know what really your options for, it's kind of hard to know what to pick. So looking through this big electronics catalog can certainly get complicated. And so that's what, I would certainly maybe I don't know any good options, but try to find a project that you can kind of follow along with, and work through that and kind of just learn what the different parts are in it, and then kind of start building your knowledge from there.
Yep. Totally.
And I know, one of the reasons we use Eagle is because it's very easy to get an educational license for it. So I think you should be able to use that.
Yep, and it also works on all softwares. KiCad does too. They may be starting to make Eagle part of Fusion 360, which Might mean we can't use it on Linux, so we might have to actually switch to KiCad, but we'll see what Autodesk ends up doing. It's a little bit farther away, but yeah, to Tan's point, check out our GitHub. Has some info too explaining it. And I just posted a link in that thread on our YouTube channel for training. It should go through how to make, should go in a lot more depth than I did, explaining how to make an entire PCB from scratch. You should be able to follow along at home. And Tan posted the GitHub page as well. So. Is there any other questions? Give it 1 or 2 minutes. I know that there's like a 20-second delay from what you all see, so feel free to ask. Yeah, I think it's super good. I mean, I didn't get an opportunity to design any custom PCBs or anything in high school, so super cool if you get that opportunity. And you'll probably learn more as you get older, working on projects and stuff like that. But personal projects is a good way to get started, for sure.
Yeah, and I mean, we definitely had a lot of fun in FIRST, and really enjoyed being able to give back to help with you guys. So hopefully we were able to help just a little bit. There's definitely a lot more out there and tons of stuff to learn, and so hopefully we just gave you a little peek to into how some of this stuff goes together. Hopefully when we can get back to competitions, we will see you all there.
Yep. All right, I think we'll sign off. All right, thanks for coming, everyone. Hope you have a good semester, good competition season, and good rest of your year. All right.